Yeah, yeah. So, hello everyone. Thank you for coming. This is the first Physics Cyrus Gems seminar of the year in 2023. Very happy to introduce the speaker of today's speakers. What did I write your name? I didn't write your name. Emma Bordier. Bordier. Sorry. I'm just really bad with French. Really, I'm very sorry. Emma, she's a PhD student at ISO and this university in Belgium. Leuven.
Yeah.
My pronunciation is falling. I'm sorry. She works on high mass stars in the context of multiplicity. So binary stars are really big and high mass. And she's from a place called La Réunion. Was that better? Okay, and she's getting better. It's an island in Africa. And she's going to be here in Chile, I mean, until next week. So this is like one of your last stops in your way back to Belgium to finish your PhD, right?
Exactly. Yeah.
So we're very lucky to have Emma today. Please.
Yeah.
Go ahead.
Thank you, Seva. So yeah, it's actually my last days in Chile. I go back to Belgium on Sunday, so I'm very happy to be here and to present a bit my work. So today I will talk about massive stars, how they form, and which technique I use to observe them, which is interferometry and high contrast imaging. So yeah, the title of the talk of today is Probing the Multiplicity of Young Massive Stars thanks to interferometry and high contrast imaging. So here at ISO, I was working with Willem de Wit, and in Belgium, I work with Abigail Frost and Uxana. Abigail, she will be working at ISO soon, so you can also get in touch with her. Okay, so I'll put some context about star formation. So here is like a very simple sketch of the life cycle of stars. Obviously, I work mostly on the left hand part of the sketch, but well, all the stars, whatever the mass, they originate from the star forming nebula, and depending on their mass, they will have like two different paths along their life. So if we first focus on low mass stars, which is really not my expertise, but I think it's worth some words. So yeah, they also originate from the star forming nebula. There are stars that are less than 8 solar mass. I will explain later why we have this cut. And we are very lucky because the formation timescale of this type of star is kind of long, so we can have an observational sequence of the formation process, and we can have an image of each of the steps of the star formation process. And something that is to be known also is that 30 to 50% of these kind of stars are in multiple systems, which is very little compared to high mass stars. So how do they form? So they originate, it's what we know, they originate from this molecular cloud called molecular cloud. Eventually, they will have some external source of energy, such as a nearby supernova explosion. And then it will start like the collapse of this cloud. And they will have like the central primordial core on which will form there will be a gravitational falling onto it, and eventually will form like a disk, and the response to the formation of this disk will be to have some outflows. So it's what they call like class 0, 1, 2, 3 here, and you end up with a solar system. So as I said before, we have quite nice observations of most of the steps of low mass star formation. So a lot of with ALMA, especially for the late stages with all the protoplanetary disks. With APEX, they could actually see the filaments that are forming. So at the very early stages of star formation, we have these very amazing image from GWST that was released at the end of last year, showing like the half-flows of a low mass star formation. And these also are sphere observations, and they show like the inner disk, but also like the outer disk of that are forming around these stars. So that was it for low mass stars, and now we jump to massive stars. So why do we care about massive stars? Is because the first massive stars are known to have contributed to the formation of the very first galaxies, and also to the reionization of the universe. Their feedback is tremendous in the interstellar medium. And that's why they are of great importance. And also they end their life as a supernova. They explode and they become either a black hole or neutron star. And we know that the study of this object has been super trendy these past years with the detection of the gravitational waves and so on. So if I can portray a massive star, so there are stars more massive than 8 solar mass. So there is this cut at 8 solar mass because we observe after 8 solar mass that these kind of stars go through the core collapse, and also like the feedback into the interstellar medium is tremendous, and they have huge mass loss rates, and so the lifetime is though very short, a few million years. So if we can put into context and put some order of magnitudes, by the time if you form here in the star forming nebula a massive star and a low mass star at the same time, by the time the sun-like star will reach the main sequence, the massive star will already be a neutron star or black hole. So we are really talking about two different scales. And the formation time scale of a massive star is 100,000 years. And this makes the observation very difficult. I mean, the observation of single steps of massive star formation, such as for low mass stars. So that's why we don't really know how they form. Oh, it's funny, I have a funny disk there. But so this theory would be like the scaled up version of low mass star formation, where you have the cloud, you form the central, the very massive star, and here there is a question mark because we don't know what happens after the disk and the outflow phase, because they are deeply embedded in a hydrogen envelope. And all of a sudden, like they blow away all this envelope and they're on the main sequence. So there is like a kind of a gap where we don't really know what happens. And the second theory would be competitive accretion. So this, the main difference between the two is that here, the mass to form the massive star is not bounded to the star from the beginning. And the gas will inflow due to the cluster potential towards the cluster center, where you will form the most massive stars. So basically, the growth of the cluster and the growth of the massive stars at the center are linked together because they will grow in the same time. There is a third theory, would be like stellar collisions, but you need very, very dense clusters, more than million stars per parsec square, for the collisions to occur and to form very massive stars. And as I said before, we do not have any observational sequence is missing, and that's why we just know little about these stars, because we have to go beyond this dusty envelope that is surrounding the stars. And on top of all of this, one of the main criterion of massive stars is that more than 90% of massive stars are found in multiple systems. So before I talked about how to form a star, but it was like a single star, and now we have like also to take into account that most massive stars are in binaries or higher multiple systems, and of course they will form at the same time as this binary. Okay, great. So why massive star formation is still poorly understood? As I said, they are decanted in their dusty envelope. They are rare and distant, and they are short-lived. And if we compare this with main star, okay, sorry, with main sequence stars, so 90% are found in multiple systems. But if we compare this with, I don't know what, sorry, it's not switching. I don't know if it's a lack of internet or. Okay, sounds like it. Okay. So yeah, there is a discrepancy when we observe populations of massive stars on the main sequence and on the pre-main sequence. So on the main sequence, we observe that there are mainly short period binaries with periods of less than months, and actually 40% of them have periods of less than weeks. But on the pre-main sequence, when we observe population of massive stars, there are rather long period binaries of several years. So we do not really know like how they can form to reproduce the short period systems that we observe on the main sequence. And this has been observed, for example, in M17. So they observed a very low radial velocity dispersion. So basically, from spectroscopic studies with X-Shooter, for example, they observed 11 pre-main sequence stars, and they could derive the velocity dispersion using the Doppler shift. And what they observe is that the radial velocity dispersion is very low. So basically, that means that they think that there is a lack for short period binaries, because if you have closed binaries, then it might increase the dispersion of the radial velocity. And they tried to convert this low radial velocity dispersion into physical parameters. And what they observed is that this low radial velocity dispersion could either be reproduced if we consider that there is a low binary fraction in M17. That is mostly unlikely because it would mean that M17 is really a different case. Yeah.
Sorry, M17 is a cluster.
Sorry, is a star forming region. So yeah, I will talk about it later. But it's like star forming region where we observe a lot of young massive stars. Yeah, and so they reproduced also to see what kind of periods would reproduce this low binary fraction, this low radial velocity dispersion, sorry, and it cannot be reproduced with a period of 8 years, more or less. So that would mean that there is a lack of short period binaries in very young regions, and one of the scenarios would be that massive stars are formed at larger separations, and then they migrate to reproduce the short period binaries that we see. So actually, we have to find a scenario to reproduce what I just said, how we can go from long period binaries to short period binaries. A colleague of mine in Heidelberg, Makla, she has done the study to know whether M17 was exceptional case in the Milky Way, or if other clusters also represent this. So you have different star-forming clusters on this graph, and she represents she shows the radial velocity dispersion as a function of the age. And what we can get from this is that the younger the cluster is, then the lower the radial velocity dispersion will be. And you see that like basically all these clusters, there is a lack of short period binaries if they are like younger than 3 million years. So that would mean that we need a mechanism that is pretty fast to actually make binaries shrinking and be left in very tight systems. So this is where was theorized the migration scenario, where binaries are born at large separations, and then they harden on a time scale of 2 million years, more or less, to get closer to the central star. So this can be done mainly between 2 channels. The first one would be that the companion interacts with the accretion disk, or the remaining disk that is around the massive star. And of course, this interaction will make the system to get closer. And the other one would be that there is actually another body, star, because we will see that they are formed with plenty of other companions that will push the second stars towards the first one, also with gravitational interactions. Cool. So now we will focus on the spatial observations, and I will show you how we can constrain the multiplicity of 6 younger stars in M17 to test this migration scenario. So basically, if we can spot companions within the accretion disk, that is a good hint that migration scenario is happening around within these systems. So first we have to choose the object. So we took M17. That was the one showing like the most surprising low radial velocity dispersion. And as you can see, M17 is a very crowded region. And especially at the center, there is a cluster that is full of massive stars. So we have picked 22 stars in these clusters. But actually, due to weather conditions that were not good, and also the sensitivity of gravity at the time of the proposal, only 6 stars out of the 22 could be observed. And of course, they were the brightest ones. So we think that they are not the youngest ones, and that most of the dusty envelope has already gone. In the literature, we would see that these stars are of luminosity class 5, so they have most likely already reached the ZAMS. And they also reported 5 spectroscopic companions around these 6 stars. Then we have to choose the instrument. So we want to detect young massive binaries, and the most important criterion is the fact that they are deeply embedded. So we need to go through this envelope, and as they peak in the infrared, then the best way to observe them is to go from infrared to radio wavelengths. So we picked infrared, and then as we want to test the migration scenario, we want to spot or to see whether detect whether there are companions or not from 1 milliarc second to 100 milliarc second environment around the central star. And for this, we need high angular resolution, obviously, because M17 is not that far. So if we convert into physical quantities, then we are probing the very close environment of the star. And as I said before, they are predefined. So gravity and the VLTI can be used with the ATs, like the small telescope, 1.8 meter, but as they are faint, we needed to use the UTs. So we combine the light of the 4 UTs. I don't know like how comfortable you are with interferometry, so I just give you some concepts. So we all know that basically the larger the diameter of the mirror is, the higher spatial resolution you will get. But at some point, like we cannot build huge mirrors because of technology problems, also the gravity. We don't know exactly like how precise can be the alignment of the optics if we have a gigantic mirror. So they had the idea to combine just small telescopes and to synthesize like a larger mirror. So this is the principle of interferometry. So then with interferometry, what we observe is basically the light that all the 4 telescopes will combine. So we get an interferometer. So there are 2 main observables that we get from interferometric observables that are the observations, that are the square visibility and the closure phase. So here is an example of the visibility. The visibility measures the amplitude of the fringes and gives you like an idea of the contrast. So this is the visibility of a binary. So if we take the binary, so we have 2-point source, we have the light coming from it, it will reproduce, it will give like a periodic signal in the interferometer. And what you can get from it, so the separation between 2 peaks will give you a measurement of the binary separation. So you have to keep in mind that all these are Fourier transforms. So if you get a small separation between 2 peaks along your baseline, it means that actually in the sky, the binary is really wide. And the other way around, if you have a pretty like big separation on the interferometer, then when it means that your binary is pretty tight in the sky. Great, and then the minimum of the visibility gives you the flux ratio between the 2 components of your system. And then there are also the closure phases. So unlike for the radio astronomy, for optical and near-infrared interferometry, we just lose the information on the phase. This is mainly due to atmospheric turbulence in optics. So a way to counter this is, instead of measuring the phase only with 1 telescope, you measure the phase with a closed triangle of 3 telescopes, and that way you just cancel out the effect of turbulence, and you can retrieve information of the phase. We do care a lot about closure phases because they are very sensitive to the asymmetries in the system that you're observing. So, for example, if you have a binary, the two stars have different brightnesses, then the closure phases will show a big signal, and we can measure that from the closure phases. Also, for example, if there is a binary system and one of the stars or the two stars have disks, this will also be shown in the closure phases signal. Great, so now you know what is closure phase and squared visibility. So I'll show you here an example, what it looks like in practice. Before was the theory, so it was really beautiful. And then in practice is a bit different. Yeah, so we had like all the 6 sources that were in the cluster, and for each of them we get the visibility, the closure phase, and other parameters, but we haven't chosen them. And the idea then is to fit and to model this observable. So we used PMOHead, that is a tool that has been developed by Antoine Méran at ISO Garchim. And yeah, so it's basically like a package that allows you to model any interferometric data. So you have building blocks, and you can choose the building blocks that you want. So 1 source, 2-point source, 3-point source, if you want to model a triple, and you can add Gaussians, you can add plenty of different mathematical elements to build your model. So what we did for all the data is that we started first with a single star to know if a single star can fit the data. Then we were adding complexity until we got a decent chi-square, what I call biodecent chi-square. So we were comparing the chi-squares between each models, and we're doing F-tests, to know what was the most likely model. So what we get from these models is the position of the companion, if we fix the central star at the position 0, and also the flux ratio. So here I show you the shape of the visibilities and the model that we could apply to them. I think that these ones are very interesting because you see that the visibility is pretty high, close to 0. Still, we see like the periodic signal, but also the closure phases were very good, were very needed in that case because the shapes were showing a lot of asymmetries. The central upper one also is interesting. It was not the easiest one because it's a bit of an exotic system, but we could fit a triple on this one. And as you can see, the separation between peaks is very small along the baseline. So the companion was actually very far in the sky, and this is like 120 separation by minute. Cool, so now I'll show you some results and what we can get from this. So all of the 6 sources were involved in multiple systems. In fact, we found 3 triples and 3 binaries. As you can see, also they span a wide range of separations. So from just 2 AU, more or less, to 120 AU. So we could spot companions like all along the separation range. So then we computed what we call the multiplicity fraction. So the multiplicity fraction tells you so how many multiple systems you have out of the total number of sources that we're observing. Of course, we had like all the sources were in a multiple system, so we had a 100% multiplicity fraction. So this is the red data point up there, and we compared it with other studies to see like if it's really consistent with other studies. I think the most important point on this would be the orange one, that is gravity collaboration work. So they did the same work as we did, but in Orion. Orion is also a star-forming region. And they also accounted just for massive stars. So basically on that plot, what matters is the mass of the primary star. We do not really care about the environment of these stars. If they are in clusters, if there are fixed stars, if they are in associations, what matters here is the mass of the primary star. And we can see like this kind of signal like cosmic signal that shows that the higher the mass of the primary star, then the higher the multiplicity fraction is. And there is another parameter that we can compute that is called the companion fraction. And so the companion fraction is a bit different from the multiplicity fraction because you actually count the number of companions out of the total number of sources that we have. So we found with interferometry 9 companions, and we also added the 5 spectroscopic ones that were reported in the literature. So this led to 2.3 companions on average, and we also we put the data point with also the other studies for comparison. And we see that like for the population of very massive stars, they have more than 2 companions on average. Great. Then something else that is interesting to actually test the migration scenario is to see like what is the range of separations that we can detect. So the data points for M17s are the red ones. So we can detect from 1 AU or 1 milliarcsecond to 100 milliarcsecond. And I've also plotted the orange data points for Orion. So we span very a wide range. We can see here that there is like a lack of signal. This is actually the sensitivity that is lacking with Gravity and Pioneer. I think that they will reach soon with Gravity, wide Gravity faint, so Gravity plus. They will be able like to fill this part of the graph for the detections. So I showed you how to form a massive star, but we do not really know when the companions they form. So there are 2 different theories. The first one is that you form companions at the very beginning from the core fragmentation, or either via these fragmentations, so later on in the star forming process. And this has been really well documented, either for low mass protostars with this observation of what they call the bretzel, thanks to this very funny shape. And they really claim in that paper that the companion here was created thanks to disk fragmentation. This image was taken from with ALMA. And then, so there is Stefan Krauss in 2017. He showed also a very interesting system using interferometry. So he combined amber and also gravity observations of this system. So both stars are separated by 57 milliardsecond. Both of them have a circumstellar disk, and the whole system is surrounded by a circumbinary disk. Yeah, and also, so the main channel that he was explaining in the paper was that the companion was actually created within thanks to disk fragmentation. And I think that there were more works about the disk fragmentation theory via simulations. So there were a lot of, especially this one, I think is the latest about disk fragmentation theories, where you form the star, then of course you form the disk, and you will have what they call the fragment epoch. So during the fragment epoch, a lot of fragments, little clumps will be created within the disk. So most of these fragments will just be accreted by the central star, or they will collide within the disk, but they will not become companions. But there is like a few percentage, I do not remember exactly, but much less than 10%, I think, that will be what they call the surviving fragments. And they will eventually go through the Segon-Larsen core, and they will become an actual companion. So in this simulation, the resolution was pretty good, but just the time of the simulation do not allow to see if this fragment will actually migrate onwards or towards the central star. But I think that he's running them right now, and he has a paper in preparation about this. But the conclusion of the paper, even though he could not go through it, is that this fragment will most likely enter the spectroscopic region because this is what we observed on the main sequence. Great. So to finish with the M17 project, so I told you that we originally proposed 22 stars. Out of these 22, actually, so they observed 6 younger stars in M17 and 2 stars that in the end they appeared not to be in M17 because we cross-checked with Gaia. And there were 2 foreground stars, but they were named because they were on the line of sight of M17, so they were named with the same nomenclature as the stars on M17. But still, like we could, I did the exact same process. So we found that the F star was a binary, the G star was just a single star. I published the results also in the paper, but so there are still 14 MYSOs that need to be observed. These 14 ones, we exactly know their classification, and they are all MYSOs. So we really want to know what happens earlier in the stages, because the ones that we observed were younger stars already on the ZAMs. So we would like to know if we can spot companions around this MYSO. So the proposal has been accepted in priority A, in P109. I don't have the data yet because they were giving the priority to the GTO of the Galactic Center people on gravity. So they have postponed the observations, and hopefully we'll have them this year or the one after. Okay, some conclusions about M17. So 100% of the stars were multiple, with 2.3 companions on average. Despite the cluster environment and age, M17 shows consistency with the previous studies in terms of multiplicity and companion fraction. And this fragmentation forms companions and provide a viable framework for migration, but the models will be better constraints when we will be able to observe the younger stars. Great. So now I would like to show you like a second project I am working on, which is to probe the wide environment of MYSO. So with interferometry, we're able to probe scales from 1 to 100 milliards. But with high contrast imaging, we are looking what's happening even further from 600 to 10,000 AU. So here you can see like how it is very important, how the complementarity of the different techniques is very important to probe all the scales around the stars and to fill the gaps in the parameter space. So with gravity, I was probing these scales with long design interferometry. And with NACO, we are probing much wider scales. So yeah, the quick summarize on the main sequence, we know that binary interaction dominates the evolution of type stars for more than 90%. On the pre-main sequence, we know that most of the stars were also found to be in multiple systems. But for the formation stage, which is MYSOs, we still do not have much clues. We have like 2 studies that have been done over the past years. The one of Robert Komahachi, who uses also NACO in the K-band. So he observed 32 objects, and he found a multiplicity fraction of 31%. So it's much lower than what we could observe on the pre-main sequence. And Evgenia Kumpia, she observed with interferometry as well. She could observe young massive stars. I think she's the first one who did that with interferometry. It's also the class of stars I am hoping to get the observation soon. And she found a binary fraction of 17%. Only 1 object out of the 6 she observed was in a multiple system. So these 2 results are showing very low multiplicity fractions compared to what we observed. So yeah, that's also where the project comes in. So I have observations of 13 MYSOs that were taken by NACO. So I got this, so they were back from 2013, the images, so almost 10 years ago. But they were taken in cube mode, so we could actually stack them and get the most out of the signal. They were taken in L prime band, so 3.8 micron, which is already in the mid infrared. And as you can see, like the scales that we are probing are much larger because 1 pixel on this image is 27 milliarcseconds. Yeah, and also, so what we could spot at first sight on these images is really like exotic systems. For example, for this one, so we can spot two companions and a third companion that is actually a binary or visual binary. And then is the same for the central star. And the last one is very interesting because we see kind of nebulosity that is also very bright in the mid-infrared around the central star. Great, so I will not show you the preliminary results because I am still working a bit on two sources out of the 15. But what we do is that for each image, we run like an automatic search for the peaks and the companions. And then from this, we want to derive the orbital parameters. So we perform some PSF fitting to get the flux of each companions. And then once we also have the position of the pixel, we can retrieve the physical distance with the primary star. Now I am like at the step where I am like putting kind of strong constraints on the infrared excess and the extension to be able to get the mass of each of the detected points. And of course, the last step would be like I would like to know what is the likelihood of each of these peaks on each image to be actually bound to the central star. So yeah, I am working still on the last two points, and I hope soon that these results will be published. Great, so some takeaways. The advent of optical interferometry and especially the VLTI helped our understanding of star formation, massive star formation. We could observe a discrepancy between the measured and Wise multiplicity and the main sequence. So the migration scenario could bridge the gap between these two regimes, but we still need some more evidence with a bigger statistical population. And we have also seen that I think is very important that even 1 million year old massive stars have companions, which is what we're observing in 17. So the multiple systems are set very early in the life of a massive star. And then massive from main sequence multiples are present in the 1 to 120 AU separation, and they show the same trend in the main sequence in terms of multiplicity fraction, combining fraction. And we have seen with other studies that the MYs on multiplicity might be a bit lower, but we are still exploring that. And then some next directions. So we've seen that developing a multi-wavelength approach is really necessary to trace all the scales, but also to trace like the disk and the gas. This is also what I would like to do with ALMA, to trace the dynamics of the gas in all these stars to know how they gain mass. And then it is necessary to observe more MYSOs to build a robust sample and better constrain the onset of multiplicity. And future instrumentation will, of course, help us to go fainter and increase the sample sizes and the statistics. And I am personally waiting for the advent of Gravity Plus and the DLT, not really, but Gravity Plus to be able like to go fainter in the MYSOs that we can observe. So, thank you.
Thank you very much, Emma, for that talk on time-mass binaries and multiples. Are there any questions for Emma?
Yes.
Can you go back to the macro observation for first? Yeah, next. Yeah, so what's the separation between the binaries? You remember it out?
These ones?
Yeah, like you resolve it with macro.
Yeah, but they are like pretty, I do not remember, but it's almost 500 AU between these two.
Okay, and
given the distance, because they also do not have the same distance, but this source is really far away, like 2-point-something kiloparsecs away.
Why do you not try observing this with other hypotheses?
Yeah, that would be actually with interferometry, I think, or interferometry would be too far, but for example, with sphere, I guess that this object would definitely be resolved. Yeah. GWST also, yeah.
And if you want to continue with L prime, I think LBGI has a now.
Which one?
LBTI, the large binoculars. They have it
Okay.
right there. But
Yeah.
NACO now, I think they have it, like NACO is not.
No, NACO is not. Now there is Aries that also has the same bands, which is also okay. Yeah, that could be interesting.
In the last image,
Yeah.
what you did because it's near infrared, right? So
Yeah, it's 3.8. This kind of nebulosity.
Yeah.
Yes, this is really strange. Like we try to explore a bit in the literature, but there is not much at this wavelength to explain this. We tried like to see whether there is other kind of disk or material, dust material that could be around, but still we haven't found any. I think we should check in the ALMA archive maybe for this region to see. Yeah. But we're actually surprised to see this kind of pattern of around the star. Also, we cannot really constrain the age of this system. But yeah, we know that it's a MYSO, so it's really young object.
Not from background. It's
No, we don't think so. We think it's really linked to the object.
There is also a difference in brightness.
Yes, it's fainter. Yes.
Yes.
Another question,
Yeah.
if the main scenario that you're explaining, like to do not have short period binaries, ISO is due to migration. What should they stop migrating if time?
That's a good question. I think it's just that they find like a stable orbit around the massive stars, but they never really stop migrating, because if you look at them when they end their life, it's actually like the collisions of neutron stars or whatever that we actually spot. So yeah, it's maybe just that the velocity at which the speed at which they migrate is might be slow down at some point, but I don't know.
Yeah. Mine is much a simpler question.
Okay.
What defines the two stars are associated? I mean, it seems that you just look for things that are very much together on the sky.
Yeah.
Well, how do you know they're bound?
Yeah. So you mean for the NACO
I
images,
mean,
or
that
even
field,
for
I
gravity?
can see that those two are probably related. It's nothing else.
Yeah.
But the other fields seem a lot crowded. So how
Yes, so there are fields that are much larger. This is actually why, so we want to perform this likelihood, but we think that at this band, at the L prime band, most of the stars that we observe on the image are actually in the cluster of the stars. Otherwise, we would see background stars, which we do not see in the L prime. I mean, it would be much crowded also everywhere. It could be like a kind of uniform, which is not the case. So, but still we're not 100% sure, so that's why we want some.
So in that likelihood that you want to calculate,
Yeah,
what are the ingredients? Like,
the problem, so
well, you haven't done it
yeah.
yet.
So we would use like the magnitudes and use like some equations. The thing is that for the L prime band, we don't have there is no literature for the L prime band. So there is for the K band. So we would like to use this K band and try to convert it, kind of try some like relation to be able to do it with the L prime band. But yeah, I'm still not really at that stage, so I'll work on it. But yeah.
Related to that, maybe isn't Gaia help to associate the stars? I mean, you can measure the distance quite exactly.
Well, the thing is that that's the problem, is that these stars are so embedded that Gaia doesn't see them because it's in the optical. So for the distance, actually, I have big error bars because I took these MYSOs from the catalog that is called RMS, and they calculated the distance. But for example, I know that it's 2 kiloparsecs plus or minus 0.8 kiloparsecs. So And this also is a big error about that, like we get when we derive all the other stellar parameters, because of course it's linked to the distance. But for Gaia, no, actually, I think I checked in Gaia, and out of the 13, there might be a detection for 3 of them, which is still not sure. But I think Miguel works in that too, like Gaia and young stars, and more.
I don't think I can. I was also curious about how you know if they're mountains.
Mm.
I mean, I believe those.
This one's, yeah.
But the other one you showed, for example, in the next slide.
Yes, these ones.
Those ones, for
Mm.
example.
This one I would be sure so, but then if this system is bound to the central star, yeah, it's not sure.
But how big is that? How big is the
It's 28 by 28 arcseconds. So I think for this one, I think it's 20,000 AU.
Marina's gonna ask that, you know.
Yeah, sure.
Okay, how does this astronomers work? I mean, we have a huge amount of observations. So you have some possibility, I don't know how it's organized, just if you isn't this so much conserved forever? I mean, in 20 years, somebody observes the same star. Can somebody access to the same image and see it again? Do you have some,
Yeah,
like,
of course, like,
this is a huge code for this star, but do you keep tracking of all previous observations?
yes, we do actually in the archive. These
All
subjects,
telescopes on the world, do you need to go to each telescope?
Yes,
Or-
only the big ones?
yeah.
Some that are colored.
Actually,
There are a few articles.
yeah, there are a few.
Few or four that are the same.
And it's really interesting what you are saying, because, for example, my colleague who observed these stars, we have 4 stars in common in the sample, and he observed his stars in 2018. And for some of them, like that I observed 5 years earlier, we can actually see that they have moved like little bit. But we will also compare with his, like how because in 5 years, like of course they will not, they are too far away, like to have they probably have like 100 even 1,000 years orbits around the central star, but you can slightly see that.
So somewhere there should be a huge service. Images.
Yeah, I have a question regarding the this fragmentation hypothesis.
Mhm.
I don't really understand, because this massive starts from really fast. So by the time that there is something going on in the case, they already should have a very strong variation.
Yeah.
So there must be some constraints to what stars can fall in this mechanism.
Yes.
Do you see that like go to me in the binary, in the mass fraction?
Yeah, actually, the stars that we derive with gravity, they are almost twin binaries. The mass, yeah, the Q is around 0.7 and 0.9, so they are really massive.
So they actually form at the same time.
Probably,
Form the same.
So no, so that mechanism. Or
most likely, yes. But it's really like a good point that you raised, is that like everything is so fast in terms of timescales that it's almost impossible to know at which stage exactly they are formed.
I think that law splitting is needed for us because it looks very similar to the laws that we use to explain planet formation, but it's a totally different mechanism. Because it's not that the stars is formed and the planets form around the whole thing.
Having the same mass constraints. Having the same mass in binaries constraints. They have the same mass, or they
it's
have
probably
different
not
mass.
captured, right?
Yeah, So
That means it's
Ah,
captured.
Yeah.
Possible. Like that, you can capture something as.
the thing is that so you have disks almost everywhere. So each star each will have its own disk, as you see. So the star will grow with this disk, but also with the circumbinary disk. So the mass accretion rates that you can get are huge, I guess. And also, if you consider that you form these stars in competitive accretion, you also have the mass from outer of the cluster that will fall onto the system. So actually, I don't know how we can form planets around these kind of stars, but because I think that by the time they explode is basically the time you need to form a planet. No, I'm not sure, but also the radiation that you have around these very massive objects probably prevents from forming planets.
So I haven't been paying much attention to the literature on the high mass star formation, but there were very little examples or evidence of detected disks around the stars, right?
Yes.
There are not that many examples, and it's not clear that they have very rotation.
Well,
Rotation, but it's a
yeah, I think that in the work of Evgenia around the moisures, she could actually use the bracket gamma line in the K band, and she has evidence that these stars have disks around. Yeah.
But the disks are also much shorter lived, right? Like they
I
accrete much
guess so,
faster,
yeah.
so then it makes it harder to get a good sample, because if they just exist for, I don't know, like 500,000 years, then it's hard to find the stars.
Yeah, to form like a gas planet, you need to be faster than 10 million years.
Oh,
Yeah, it's like these
Yeah.
fragments. What happens to them? Like, can you form a Roma star with them, or it's not enough?
yeah, I think that it's actually the conclusion of his paper, but he says that then the fragments, most of them will just be accreted and hidden by the central star. Yeah, by accretion, like epochs and processes and events, a lot of accretion events that will just drag all the fragments towards the central stars. But eventually you will have some fragments that will survive. They will grow also, and if they are massive enough, they will also have a disk that will be created around them, and they will grow that way also. So, but with this scenario, I think the conclusion was that you form mainly low mass or intermediate mass companions. We do not know how we form twin binaries with this mechanism.
As in, okay.
Yeah, of the
As in
same mass, like two very big. Yeah.
If you have stable, big enough and stable enough fragments, and you're saying that in the paper that they can form the disk, but from what? Because the material should already dissipate, right? They have already dissipated, like circumstellar.
Well, this happens pretty much. I think that in his simulation, this fragmentation epochs occurs 200,000 years after the collapse of the. Yeah, it's pretty fast. Yes. And these epochs like last pretty long also, until the central star just blows away everything. The disk and the envelope and enters the main sequence.
Are there any questions from the room? People? So unless there are more maybe if you guys have another question, we can continue talking with Emma after the close here. So I wanted to thank you again for coming.
Thank you.
Good luck going back Europe to finish your PhD, and thank you everyone for coming.